Hi, in this video we will learn about an application of derivatives when we are trying to find limits and when we have indeterminate forms of type 0 over 0. This is called Labtube rule, and it is one of very nice applications of derivatives. So let me start with recalling that when you have a function, well, two functions, f and g, which have both of them as x approaches to a have limit 0, then the limit of f of x over gx as x approaches to a, well, right away when you look at that, you say, okay, I can use the quotient law. No, you cannot, because the limit of the denominator is 0. This is even worse than that. The limit of the numerator is also 0. So these guys cannot be evaluated right away. You have to do something, and these have a name. It's called, then is called an indeterminate form of type 0 over 0. 0 over 0 is not a number, so it cannot be the value or a value of a limit. But we have a name so that we can deal with this kind of limits. Well, we already saw that when you have a polynomial over polynomial, you factor out the vanishing factor from numerator and denominator, and then cancel them. Then you will find the number better limit. Yes, but there is a nice trick here that we can turn this limit into a limit which involves some derivatives. Okay, I will just give you easy case that if further we assume that if f and g have derivative at a. So it means that, well, they are continuous at a, and as a result, you know that limit of f of x as x approaches to a is going to be equal to f of a, but we already know that this limit is equal to 0, so f of a is going to be 0, and with similar argument, g of a is going to be equal to 0. Now that we have limit of f of x over gx as x approaches to a, we can rewrite this limit as f of x minus f of a. Why you can do that? Because f of a is 0. I can add, you subtract from anywhere, you don't change that number, yes? And in the numerator also we can write gx minus ga as x approaches to a. And now, well, I need to have the limit there. Since we're trying to find the limit, and the limit never sets x equal to a, so x minus a is going to be always not equal to 0. So that means that we can divide both numerator and denominator by x minus a. So here will be f of x minus f of a, and g of x minus g of a. Well, you look at the numerator. The limit of the numerator as x goes to a is exactly f prime of a, and limit of the denominator as x goes to a is g prime at a. Now, for example, if g prime at a is non-zero, then we can go ahead and right away find the limit of numerator, which will be f prime of a, and limit of denominator, which will be g prime at a, and divide them. That will give you the number there. But here I'm assuming that f g prime of a is non-zero, but I don't need to assume that, and the more general and a little bit more complicated proof of this will tell me what is called L'Hopital rule. L'Hopital's rule says that, okay, assume that f and g be differentiable functions, and assume that g prime of x is non-zero in at least in the neighborhood of g, in neighbor of a, sorry, except probably x equal to a itself. So g prime at a can be zero, but we need to make sure that f over g prime is non-zero in a neighborhood of a. And okay, further, if limit of f as x approaches to a is 0 and limit of g as x approaches to a is equal to 0, then L'Hopital rule says that now that you have this indeterminate form of type 0 over 0, you can replace it with another limit where the numerator is replaced by f prime, the derivative of the numerator, and the denominator is replaced by the derivative of the denominator. This is called a L'Hopital rule. And basically, this takes care of that canceling the common vanishing factor x minus a automatically without you being involved in any of those factoring and canceling. It will do it automatically itself. Okay, let's do some examples. Very nice. Find the given limits. First of all, we see that it's polynomial over polynomial, and limit of the polynomial in the numerator as x approaches to 1 is 0. Limit of the polynomial in the denominator as x approaches to 1 is also 0. So we have an indeterminate form of type 0 over 0. Note that 0 over 0 is not value of the limit. 0 over 0 does not make sense. It's not a number. It is an indeterminate form. So the numerator and denominator can be differentiated. So we can use L'Hopital rule. And what does it say? L'Hopital rule says that when you have indeterminate form 0 over 0 and your functions are differentiable, you differentiate numerator and replace the numerator by its derivative and denominator by its derivative, and then find the limit of. Now you see limit of the denominator is 2 times 1, so it is, we can use the quotient law, and in this case actually we can have this thing negative 1 over 2. You see, we didn't see any factoring and canceling vanishing factors. It did happen automatically when we use L'Hopital rule. Well, L'Hopital rule shows itself even in very a better way when you have more complicated functions which are not polynomials. For example, cosine x minus 1 over x squared. There are some tricks that you can find this limit without L'Hopital rule, but with the L'Hopital rule, you can easily do this one. First of all, you notice that it's 0 over 0. And these are differentiable. We can use the L'Hopital rule, means that replace the numerator by the derivative of the numerator and denominator by the derivative of the denominator. Very nice. We change our limit to another limit, and the result of these two limits are going to be equal. But when you deal with this new limit, again, you have fraction or quotients of two functions, and you know that sine of 0 is 0 over 2x as x goes to 0 is 0. So this is also another indeterminate form. But we know that the numerator and denominators are differentiable, so we can use L'Hopital rule to change this limit to another limit. The numerator, which is minus sine x, it can be replaced by minus cosine x, which is derivative of minus sine x, and the denominator can be replaced by the derivative of 2x. Now we have very good continuous function. Just evaluate and you get negative 1 over 2. So L'Hopital rule told us that our original limit is equal to the second limit here, and then another time L'Hopital rule helped us to turn our limit to even easier limit where we can compute without doing any other work, just subbing in. Okay, in the case of the last one, I believe there is no easy way for you to do this without L'Hopital rule. Exponential function and tan, these are different and difficult functions to deal with. But when you find the limit of x as x goes to 0, the numerator gives you 0, the denominator gives you 0, so we have an indeterminate form of type 0 over 0. We can use L'Hopital rule because both functions are differentiable at 0, and well, derivative of e to the power x minus 1 is e to the power x. Derivative of tan x is secant squared x as x approaches to 0. Now, when you look at the denominator, the limit of the denominator cosine secant x, which is 1 over cosine x, as x approaches to 0 is 1. So we can use the quotient law. This will be 1 to the power 2. This will be e to the power 0, which is 1 over 1. It is 1. And again, as you see, whenever we have 0 over 0, I never write it in front of the equality because 0 over 0 is not a value. This is just a form. We have to see it and do something. What is the trick we can do here is L'Hopital rule. You can do L'Hopital rule and change the limit to another limit and hope that the new limit will be easier. And if the conditions of L'Hopital rule continues to hold, you can repeat that as far as you get 0 over 0, how many times you like.